Good evening, everyone. Welcome to today's presentation. Today, we'll be looking at the topic Achieving Safety Through Design, Technical Safety Perspective. I'm Chike Emmanuel Abba, and this is my outline. I'll be looking at why does it matter, two aspects of safety, technical safety, plant layout, hazardous area classification, drainage systems, process safety systems, fire and gas detection, active and passive fire protection. So we go to why does it matter? By way of introduction, I would like to address an all-important question: why does it matter? So the best way to examine why process safety matters is to look at what happens when things go wrong. While we bemoan the Piper Alpha incident as shared in last month's meeting, it's imperative to note that we have a lot of pockets of Piper Alpha that occurs here in Nigeria. The NMPC disclosed that from 2001 to 2019, Nigeria has witnessed 45,347 pipeline breaks. And definitely we know that these breaks are usually accompanied by explosions. I tried to capture some of the major explosions the country has recorded so far in the table below. We have the gas station explosion that took away 10 lives and destroyed 41 buildings in Barawa, Lagos State. We have another gas tanker explosion that injured 44 persons, destroyed 36 buildings, and also destroyed 26 vehicles in Ifako Ijaye, Lagos State. We have a fuel tanker explosion that took away more than 25 lives, destroyed 10 vehicles in Lokoja. And we have the Betiokun oil field OML 40 explosion that had 7 casualties in Niger Delta. And we have of course, the controversial Abuledo Lagos explosion that took away 23 lives and displaced 276,000 persons, destroying 50 houses. So when we look at the severity of what happens whenever an accident takes place, lives are lost, resources are wasted, and it becomes imperative that safety of processes be taken serious. So the DPRU initiated steps to compel fuel marketers and gas plant owners to meet its minimum safety training requirements or lose their operating licenses. I read up that they said they will be starting on September. I don't know how far about now. So I believe their decision was born from a discovery that 70% of accidents in Nigeria oil and gas industry between 2013 and 2019 occurred in the downstream sector, including falling tankers, petrol station fires, gas explosion, and vandalism. So we look at two aspects of safety. You have the personal safety. If personal safety is more of solo, is potential to injure one person, and it occurs basically due to an individual carelessness or maybe an unsafe condition. You have the likes of slips, trips, fall, electrocution, and the casualty is usually limited to one person at most times. And then we have the big one, the process safety. So hazards in process safety involve major accidents. Talk about flammable reactives, explosive or toxic materials, and the release of energy such as fires. So whenever there is a process safety breach, it always leads to multiple fatalities, and most times it can also result to environmental damage. So we talk about common hazards in process safety. When there are spec breaks in the wrong location, when the minimum temperature expected for materials are not specified, and the codes are not met, wrong piping and fittings are used, tanks and vessels don't meet the regulatory requirements, when sizings are not done properly, equipments are not properly spaced, when buried lines at production facilities are forgotten, and when measures of corrosion control are not put in place, and when systems are weakened by high temperature, and when we also have high stress due to dilation or bad supporting, we have corrosion, equipment aging, erosion of internals due to sand or high velocities of the fluid, and runaway reaction. These are some of the things that poses a hazard in a process plant. So we now talk about technical safety. What is technical safety? So technical safety comprises a set of discrete elements that are applied in the field of risk analysis and management. And what they do is to help identify, to understand, and evaluate, and to specify solutions necessary to reduce risk to levels as low as reasonably practicable. So how does the technical safety achieve this hazard prevention or mitigation? They do that through quality assurance and quality control during design and construction, through early detection of plant upsets, overpressure protection, pipes to be protected from mechanical failure due to vibration. They do that through correct fail-safe position of control elements, where components are designed so that when they fail, they have the minimal possible impact, through the proper sizing, explosion protection, and specifying safety integrity level. So we look at some of the approaches adopted by technical safety to achieve these things. The list is not exhaustive. I'll be looking at plant layout, hazardous area classification, drainage systems, process safety systems, control alarms, blow down and shut down systems, fire and gas detection, active and passive protection, fire protection. So we look at plant layout. Installations and piping routes are designed so that their location possess minimal risk to people, environment, and material assets. And also important that living quarters, control centers, and equipment of major importance to safety are located from far as possible from hazardous areas. Most times we use a blast resistant buildings for control rooms so that no matter what goes wrong, we can be able to still control a number of components in the plant. So we also make sure that plant layouts are so that escape routes provides minimal time for escape to safe areas. So we now talk about escape routes. Escape routes. How do you design? What do you consider when designing an escape route? Talk about the time for escape. So the time needed for escape to safe area, including time for safe termination of critical tasks, rescue operations, shall be estimated, and efforts shall be made to minimize this time. And for number of exits, it's required that at least 2 exits, 2 escape routes should be provided. 2 exits should be provided for regularly manned areas. And for door swing, doors shall normally open in the escape direction, but not block the outside escape route. And it's also necessary to make sure that the doors are not electrically or pneumatically controlled, because most times when there are explosions in plants, you can knock out the electrical system. And if these doors are electrically controlled, that means exit will be difficult. So we talk about dead end corridors. Dead end corridors more than 5 meters are not acceptable when designing an escape route. And lifts also should not be a part of the escape system, because when there's a power outage, lifts cannot be operated. Then for illumination and lightings, it is necessary to make sure that the escape routes are properly lighted. And then markings, special markings are done on escape routes so that a frightened someone can be able to easily leverage on the colors and know where to run to. You can see an example of a yellow marking giving a description of an escape route in case of an incident. So we talk about hazard mitigation using a hazardous area classification. Hazardous area classification. So explosions occur when a flammable atmosphere is met with an ignition source. So what hazardous area classification tries to do is to classify areas of plants that are potentially affected by explosives. So what HAC does, it allows for installation of suitable electrical equipment and instrumentation. So for areas that are highly volatile, the components used there are such that there will be no spark at all. So for thermal explosion risk management, the hazardous areas are classified into 3 zones. And we have zone 0, zone 1, and zone 2. So for zone 0, these are locations where ignitable concentration of flammable gases or vapors are present continuously for a long period of time. And when these ignitable concentration are only available under normal operating condition, we classify those ones as zone 1. But when this ignitable concentration of flammable gases or vapors only occur for a short period and not during normal operation, we classify that as zone 2. So we look at drainage systems. So drainage systems are used to safely dispose of liquid spilled drained from equipment or resulting from washdown activities in oil and gas processing facilities. So a drain system that is connected directly to a pressure vessel is called a pressure or closed drain system. And a drain system that collects liquid that just spills on the ground is an atmospheric, gravity, or open drain. So open and closed drain should be completely independent from one another. And a closed drain should always be routed to pressure vessel and should never be connected to an open drain. So why do we route a pressure vessel? So why do we do that routing to a pressure vessel? That's for closed drains. It is because it is assumed that a closed drain valve could be left open by accident. So once the liquid has drained out of the vessel, a large amount of gas will flow out of the vessel into the closed drain system. And you know that's a gas blow-by, and it needs to be handled safely. So a closed drain system is recommended if the liquid being handled contains dissolved gases that flash in the drain system and can become a hazard if they are not properly handled. So we also have that this waste and other disposables should be properly treated before disposal. And also talk about drain cleaning. Drains should be properly cleaned and should be designed so that it's a cover that can be lifted for proper cleaning. And environmentally, it is also necessary to design drains such that we minimize direct discharge of polluted streams into maybe the rivers or into the environment, polluting them. So now we talk about process safety systems. Process safety systems. So emergency shutdown systems, what do? They comprise of sensor, logic solver, final element. And what they do is to be able to detect potentially hazardous condition and react to it by shutting the system down to protect the personnel, facilities, and even the environment. So emergency shutdown is normally done by monitoring the state of the field-mounted sensors, valves, trip relays, and inputs to a control system, such as alarms. So the control system is able to determine a cause and effect type analysis, which are determined to protect the facility. So when the emergency shutdown does not need to completely shut down the entire plant, because sometimes completely shutting down the entire plant can even be more dangerous. So what the system does is to minimize the effect. So it could be to reduce the number of plant items available or shut down some given section of the system. So some of the application is a hydrocarbon inventory isolation system. So what it does is to isolate hydrocarbon systems. And we also have the emergency ventilation system. So when we have something like a smoke detection system, if a fire is detected, the system will likely shut down all plant equipment to contain the fire, not allowing oxygen in to allow it to burn. Then if it detects a smoke, what it will actually do is to make provision to vent out that smoke. We also have the safety integrity level. Safety integrity level is a system that classifies processes based on risk and probability. So we have levels 1 to 4. Levels 1 represent the integrity required to avoid a relatively minor incident and is likely to be satisfied by a certain degree of fault tolerant design using design guidelines. So for level 2, we talk about avoiding more serious but limited incidents, some of which may result in serious injury or death to one or more persons. Level 3 is required to avoid very serious incidents involving a number of fatalities. Then level 4 is required to avoid complete disastrous accidents. That's that about that. Then fire and gas detection system. What they do, they safeguard life and property. How do they do this? By providing early warning of hazardous condition, providing opportunity for evacuation and notification for re-entry. They provide time for intervention and correction. They also trigger facility protection systems like ventilation, water mist, fire suppression. So the chart below shows some of the way fire and gas detection takes a decision. There's a voting system determining the nature of action to be taken. So we talk about fire protection. We have active and passive fire protection. So what active fire protection does is to try to reduce the effect of fire. It does this by cooling of the hydrocarbon equipment, shielding against radiation, fire suppression, and it can be activated by the fire and gas detection logic or manually. And some of the examples of active fire protection system we have are fire pumps, ringman, dilute valves and nozzles. And the type of fire protection, active fire protection system you choose will depend on what is required to do and the nature of the fire it is to extinguish. So we go to passive fire protection. Now, the active fire protection possesses the purpose is to detect, alert, and seek to eliminate a fire hazard. But the fire protection system, which is passive, work in a different way. They do not need an external activation, nor do they necessarily try to extinguish the fire. They are mostly geared at preserving and protecting the structures for as long as possible. So when they are doing this protection, it helps to sustain the structural integrity during the fire outbreak, and it gives occupants longer time for escape and also gives room to fight the fire. So mostly what they do, the concept of passive fire protection is for fireproofing. And this fireproofing can be achieved by different methods, can be by concrete encasement. So concrete is one of the most popular because of its good resistance to heat, is non-combustible, and it has slow rate of heat transfer. So we also have the board facing, the protection systems are listed below. Also have the board facing and sheet materials. We also have the spray protection. It uses material like gypsum and cement and mixed with other compounds, and then are sprayed on those structures to make them resistant to fire. We also have the flexible blanket systems. They utilize ceramic fibers and ceramic fiber products for insulation. Then we also have the intermittent coatings. These intermittent coatings, they're actually materials that increase their volume under the influence of fire, and they create a thermal insulating barrier with low thermal conductivity on the surface of a structure. So the barriers separate the flame from metal, and significantly they retard the heating up of the metal, and it allows for saving the structural integrity of the component being protected over time. So we now go to conclusion. Although incorporating safety in design may attract additional costs in terms of money, time, and even complexity, the benefit derivable cannot be overemphasized, because it can just take one accident to raise down a plant. Then it can also take just one accident to even wipe out the whole profit made from that plant from the inception. So because most of the time when we consider the cost of incorporating fire protection and other process safety components, it appears as if it's more cost effective to avoid them. But when actually an accident takes place, it might be irrecoverable because the plant might be lost or the profit lost through litigations and compensation. And then it also might just take one accident to maim someone for life. People have sustained life injuries, lost legs, hands, sight because of accidents. And the one we don't even want to hear is when it takes life. That is why it's necessary to incorporate process safety in the preventive method when doing design, instead of always fighting the disaster when it has come, because sometimes it comes without warning. So this is just the presentation. Thank you. Any questions?
Yeah, that was great.